Dear teachers and students, good morning everyone. The title of our paper is Can Reinforcement Learning Enhance Social Capital? Then I will introduce the paper from the following aspects: introduction, problem setup, algorithms, experiments and discussion, and future work. Social networks grant individuals with both tangible benefits, for example, economic resources and human resources, and impalpable advantages such as social support, information control, and social influence. The concept of social capital epitomizes various incarnations and benefits obtained via engaging in and maintaining social relationships. The reward theory of attraction in social psychology, indicating that people like those whose behavior is regarding to them or whom they associate with rewarding events, points out approaches to this question on a fundamental level, which asks how would an individual take a technique to gain social capital. Prominent differences of origins divide researchers on social capital into two dimensions. Bonding social capital depicts the aggregate social benefits that an individual draws from its neighbors, while bridging capital rises from brokering devices. Community side captures an individual's potentials over acquiring opportunities and information. Several assumptions are naturally derived from this theory. Since rewards are typical of hindsight, an individual demands learning from experience via trial and error. An individual has limited abilities to establish and maintain relationships, since if otherwise trivially she can link to all others to maximize rewards. An individual gives a priorities to surrounding persons on creating links, as it is difficult to access to and gain rewards from remote parts of society. Bonding social capital is inclined to the collective resources generated by the strong relationship between group members. This kind of collective resource is generated by the social cohesion of the agent. We measure such kind of cohesion using a personalized PageRank index, which is adapted from PageRank that evaluates structural proximity between nodes through predicting the likelihood of edges between any pairs of the nodes. We first investigate the optimal Q-learning algorithm, OQL, that uses two-level ego networks as states and nodes as actions. The reward is defined as the difference between mixed capital between two time types. However, OQL is impractical for most of the time, as the space of two-level ego networks is typically too large to learn from. Therefore, we propose a fast Q-learning algorithm, FQL, that directly uses time steps. The agent V and the action A are set as node 113 and 56 respectively. Red nodes represent V's initial two hop neighbors. Green nodes in the left figure represents V's new two hop neighbors after linking to node 0 at round 1. Blue nodes in the right figure represents two hop neighbors after linking to node 11 at round 1. This picture captures the results of applying 2Q learning algorithms on football network. The line shows the median over 10 independent runs. Tendencies of social capital are plotted in this figure. Thanks to the fast stabilization, FQL surpasses OQL in the speed of enhancing social capital. More surprisingly, FQL stabilizes at a near optimal value of mixed capital, as shown in the right part of the figure. Therefore, it is explicitly that FQL successfully achieves a shade of between efficiency and accuracy in this case study. The values of social capital shown in the figure are averaged over 10 independent runs. We make two discussions. The first is a centralized network structure can increase learning efficiency. Stabilization in ER networks requires a large number of episodes. While both types of social capital in BA and WS stabilizes very fast, and the second is a centralized network structure can enhance the effect of learning. Bonding and bridging capital in BA and WS networks stabilize faster than EA networks. This can be explained from the aspects of network structure. BA networks have one and multiple centers. Nodes in WS networks are connected densely, while nodes in ER networks are randomly and loosely connected. This captures the fact that an individual can first learn to access to some center nodes in a densely connected society, but fails to remarkably enhance social capital in a chaotic and loosely connected society. Following the same citing of experiments on synthetic networks, we next simulate NB processes on three real-world networks: friend, email, and Bible. The results on three real-world networks are illustrated in the figure. Analogies to the results in random networks, the performance of the learning exhibits in a positive relationship between the clustering coefficients, a measure of the extent to which nodes in a graph tend to a clustering together. Ideas and methods proposed in this paper present a novel research initiative. There are several potential directions for future work. A fairly straightforward expansion is to explore learning algorithms to gain social capital in evolving networks. Another future challenge is to exploit representative learning and deep reinforcement learning to our model for predigesting the observation and transferring learned knowledge to other networks. A third future work is to investigate the emergence of social patterns where multiple agents simultaneously learning to gain social capital. That's all. Thank you for your listening.